Hello again from Digicool Things. I'm currently working on the design of my first I/O card for the Minimalist Europe Card Bus. As mentioned in my previous video, my intention is to make a purely Motorola based I/O card, to stay true to my first CPU card, which is Motorola 689 based. Staying true to using the Motorola peripheral chips of the early 80s means we will also need a baud rate generator for the MC6850 Asynchronous Communications Interface Adapter chip, ACIA. Unlike the more commonly used MOS Technology 6551 ACIA, the original Motorola 6850 does not include an on-chip baud rate generator, so it's necessary to generate the transmit and receive clocks externally. With the 6850, you need to supply a clock that is either 16 or 64 times the desired baud rate. A divide by 1 option is also available, but this requires the clock transitions to be synchronized with the data stream, whereas for the divide by 16 or divide by 64 options, the MC6850 does feature internal clock synchronization to the data stream. Therefore, the divide by 1 option is really only useful in an application where you are receiving a data stream that includes a synchronized clock signal. Taking a look at my original early 80s YRAP 689 Euro card, the baud rate generator was created using a 2.4576 MHz crystal, a couple of resistors, a TTL 7404 hex inverter, a CMOS 4040 12-stage ripple counter, and an 8-way dual inline switch. Here is the circuit, which, as I've no longer got my circuit diagram, I've recreated by reverse engineering my original YRAP board. These commonly available components, together with different crystal frequencies, were typical for a baud rate generation circuit of the early 80s. For my updated I/O card, I want a simplified and cleaner design, and perhaps also just making do with 4 baud rate options instead of the 8 that I originally provided. So here is an updated circuit that I've come up with. In place of the 2.4576 MHz crystal, resistors and the TTL 7404 hex inverter, I'm instead using a self-contained TTL 4.9152 MHz crystal oscillator. This frequency is twice the original crystal frequency, but 4.9152 MHz oscillators are more commonly available. Then, in place of the original 16-pin CMOS 4040 ripple counter, I'm instead using a 74HCT393 dual 4-bit ripple counter, which also comes in a smaller 14-pin package. Finally, I use a smaller 4-way dual inline switch for selecting 3 of the common faster baud rates of the period, being 9600, 19200 and 38400 baud. I was tossing up between making the 4th selectable speed the more expected 4800 baud, or whether to select a higher speed instead. Given that it's unlikely I'll actually use anything less than 9600 baud, I decided to make the 4th baud rate the less common 76800 baud, being twice the 38400 rate. Assuming we use the divide by 16 MC6850 clock option, that means we will need 153.6 kHz for 9600 baud, 307.2 kHz for 19200, 614.4 kHz for 38400, and 1.2288 MHz for 76800 baud. These frequencies equate to the 4.9152 MHz oscillator being divided by 32, 16, 8 and 4. By wiring the 74HCT393 dual 4-way ripple counter into a single 8-way counter, that gives us 8 possible outputs to select from, ranging from a divide by 2 through to a divide by 256. So this updated circuit gives us a more compact, 3-component only, retro-friendly baud rate generator for for the MC6850 ACIA. But before I dive into manufacturing a PCB containing the circuit, I thought I'd do the right thing and first verify the circuit on a breadboard. All we need is the crystal oscillator and a 74HCT393 chip, and then we'll check the outputs we want to use with our oscilloscope. So here's my simple circuit on a breadboard. Now let's pair it up, and we'll hook up the scope and see if we're getting what we want for our required baud rate frequencies. So first I'll hook up earth, and first I'll check the output of the oscillator. Right, so we're getting the correct 4.9152 MHz that we expected. Okay, so on pin 4, we're getting the expected divide by 4, which is 1.2288 MHz for 76800 baud. On pin 5, we are getting the expected divide by 8, which is 614.4 kHz for 38400 baud. Then pin 6, we are again getting the expected divide by 16, which is 307.2 kHz for 9200 baud. Finally, on pin 11, we are getting the expected divide by 32, which is 153.6 kHz for 9600 baud. So all is looking good. So next I'll get on with finalising my MECB I/O card schematic and PCB layout. Once this is done and I've received my first prototype PCBs, I'll be back to present and test my first I/O card for the Minimalist Europe Card Bus. Until then. That's it. Thanks for watching.